In today's lesson, we'll be learning how to solve problems using quadratic equations. In our first example, the formula h equals negative 1/2 gt squared plus vt plus h can be used to model the height of a projectile, where g is acceleration due to gravity, which is 9.8 meters per second squared on Earth, v is the initial vertical velocity in meters per second, and h is the initial height in meters. The subscript of 0 stands for initial. As you can see, our formula is in standard form. And this indicates that our a value is going to be negative, which means the parabola is facing downwards or frowning. It will look something like this. This should make logical sense since a projectile travels like this in real life due to the force of gravity. What goes up must come back down. In part A, we want to create a model for the height of a toy rocket launched upwards at 60 meters per second from the top of a 3-meter platform. Model is just a fancy word for equation. The other key pieces of information here is the initial vertical velocity of 60 meters per second and the initial height of 3 meters. Let's begin by rewriting the formula that was given to us in the question, which was h is equal to negative 1/2 gt squared plus vt plus h. We already know the initial vertical velocity, and we also know the initial height. However, this variable of g is actually a constant. On Earth, the acceleration due to gravity is always 9.8 meters per second squared. Therefore, I'm going to sub in my known values. So g I'm going to replace with 9.8. The initial vertical velocity I'm going to replace with 60. And the initial height, I'm going to replace that with 3. We can simplify negative 1/2 times 9.8. That becomes negative 4.9, and I can just remove the brackets from these other values that I subbed in, and you'll see a quadratic expression in standard form. In part B, we want to find out how long would the rocket take to fall to Earth, rounded to the nearest hundredth of a second. Before we begin, let's do a rough sketch. If you recall, the rocket is launched from a 3-meter platform, so it is not coming from the origin, it is coming from 3 meters. We already know that the initial height was 3 meters. However, we want to figure out how long it takes for the rocket to fall to Earth. So we want to figure out what that is. In other words, we want to find the x-intercept, one of the x-intercepts of the parabola. And don't forget that on the y-axis you have height, and on the x-axis you have time. Let's rewrite our equation from the previous question. If you recall, there are two different methods of finding the x-intercepts. We can either try and factor this quadratic expression, or we can use the quadratic formula. I would highly suggest you use the quadratic formula since these numbers are very difficult to work with. If we want to find the time at which the height of the rocket is 0, we need to write sub height is equal to 0, because that is when it is landing back on Earth. Instead of h, I'm going to replace it with a 0, and everything else stays exactly the same. If we're using the quadratic formula, we need to figure out what the values of a, b, and c are. That would be a, that would be b, and this would be C. Don't forget that the signs are included. So A would be negative 4.9. B would be positive 60. I'm not going to write the plus sign in though. And C would be positive 3. At this point, we just need to sub these values of A, B, and C into the quadratic formula. And I'm going to do that over here. The quadratic formula is x is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. You do not have to use the variable of x, since on the x-axis we are actually using t for time, but it doesn't really matter. Next, let's sub in our known values. So instead of writing b, I'm going to write 60 in brackets. And instead of writing a, I'm going to write negative 4.9. And instead of c, I'm going to write 3. Next, we need to simplify this expression. You have to be very careful and use BEDMAS. What I'm going to do is I'm going to apply that exponent. I'm going to multiply these terms out, and I'm also going to multiply these two terms out. The negative 60 stays the same. 60 squared is 3,600. Negative 4 times negative 4.9 times 3 is positive 58.8. And in the denominator, 2 multiplied by negative 4.9 is negative 9.8. Next, I'm going to add these two numbers together. Let's make a little bit more space. So 3,600 plus 58.8 is 3,658.8. Next, I'm going to apply this square root, and you have to be careful because you will get a negative and a positive answer. The square root of that number happens to be 60.496. There are quite a few decimals, but I'm just going to take 3. So now we're going to have to use this plus or minus. So negative 60 plus 60.496 is 0.496 over negative 9.8. While negative 60 subtract 60.496 happens to be negative 120.496 over negative 9.8. So over on the left, 0.496 divided by negative 9.8, you're going to get approximately negative 0.05. Remember, we're rounding to the nearest hundredth. Or we're going to get negative 120.496 divided by negative 9.8, which happens to be approximately 12.29. You have to make sense of these two numbers. Clearly, you cannot have negative time. So it will take about 12.29 seconds for the rocket to land back on Earth. So this is the value that we're going to accept. And let's just do a quick therefore statement. Therefore, the rocket will take 12.29 seconds to return to Earth. As you can see, it is very important to do a sketch and make sense of your situation because, as you know, sometimes both x-intercepts do not have an actual meaning in real life. In part C, we want to find the maximum height of the rocket rounded to the nearest meter. Again, we're going to do a rough sketch of our parabola. On our y-axis, we have height, and on our x-axis, we have time. We already know that the initial height of the rocket is 3 meters. We found out that this x-intercept was approximately 12.29, and we also found the other x-intercept, and this was negative 0.05. What we want to figure out now is the maximum height of the rocket. In other words, we want to find that. We want to find the vertex, basically. Our strategy should be to find the x-coordinate of the vertex, then sub it back into the original equation to find the y-coordinate of the vertex. You can find the x-coordinate of the vertex using two different methods. You can take the x-intercepts, add them up, then divide by 2. So I'm going to do that. So negative 0.05 plus 12.29 divided by 2. So negative 0.05 plus 12.29, you will get 12.24. You're going to divide that by 2. And that should give you 6.12 approximately. However, there is another way of finding the x-coordinates of the vertex, and I'm going to show it to you right now. It uses a fancy formula that we saw when we first learned the quadratic equation. It looks like this. X is equal to negative b over 2a. In our previous question, we already determined that b was 60 and a was negative 4.9. This came from the standard form of the equation. So let's sub these values back in. So instead of b, I'm going to write 60, and instead of a, I'm going to write negative 4.9. Let's make a little bit more space for ourselves. So the numerator stays the same. I can just take the brackets out, and 2 multiplied by negative 4.9 is negative 9.8. Once you divide these two numbers, you will get approximately the same answer, which is 6.12. So as you can see, there are two different ways of finding the x-coordinate of the vertex. Since we have the x-coordinate of the vertex, we can just take this number and sub it back into our original equation to find the y-coordinate of the vertex. In other words, the maximum height. So instead of t, I'm going to sub in 6.12. The next couple steps would be simplifying this expression. Don't forget to pay close attention to bed mass. Your answer should be approximately 187. Remember, we wanted to round to the nearest meter. Let's do a quick therefore statement. Therefore, the maximum height is 187 meters. In part D, we want to figure out over what time interval is the height of the toy rocket greater than 150 meters, round to the nearest hundredth of a second. The first thing you should do is do a rough sketch. We want to figure out at what times the rocket is at 150 meters. Height is on the y-axis and time is on the x-axis. Basically, we want to figure out this and this. We're going to begin by rewriting our equation. Since we want to figure out the times at which the rocket is at 150 meters, we're going to sub the height as 150 meters. So instead of writing h, we're going to put 150, and everything else stays the same. Next, we want to collect like terms. So we're going to move the 150 to the other side of the equation. The left becomes a 0. And basically you have positive 3 and negative 150, which is negative 147. To find the values of t, we can either factor or use the quadratic formula. I would highly suggest to use a quadratic formula once again, since these numbers aren't the easiest to work with. So our a value is negative 4.9, our b value is positive 60, and our c value is negative 147. So let's just write that down. I'm just going to make a little bit more space for ourselves. At this point, we want to rewrite our quadratic equation, which is x is equal to negative b plus or minus b squared minus 4ac over 2a. What you're going to do is take your values of a, b, and c and sub these into the equation. After, you're going to simplify using BEDMAS. You are going to get two values of t if you've done this properly. I'm going to skip all of those steps since you've already seen how to use the quadratic formula. And you should get a value of 3.39 or 8.86. Since these are both positive values, that means we can use both of them. They have a meaning in real life. Let's do a quick therefore statement. Therefore, the rocket reaches 150 meters at 3.39 seconds and 8.86 seconds. The reason for that is obviously the object, once it goes up, it's going to have to return back to Earth due to the force of gravity. So it is going to reach a height of 150 meters twice.